You guys are all here to carry on the people that are going, right? All right. So if we're doing a limit problem without a calculator, what's the first thing we do? Think about the videos we watched last week. What's the first thing we do? Substitute, right? Substitution. So the very first thing you always do is substitution, because that might be the answer, right? If x is approaching 3, put a 3 in for x. If you get out a number for the ones we're doing, if you put in a 3 and get out a number, you're done. That's your answer, right? That's your answer. Now, you might say, well, wait a minute. I thought you said that the y value is not necessarily the limit, like on this problem right here, right? At -3 on your homework, right? What's the limit at -3? The limit as x approaches -3, the limit is -1, because that's where the cars meet, right? That's where the cars meet. The diner burned down, and they built a new one somewhere else, but we don't care. The cars meet at -1. Okay, that is the limit. But what's the y value at -3? It's the y value of the function. What's f of -3? 1, right? F of -3 means if you put in a -3, what do you get out? You get out a 1. Okay, but here's what I'm telling you. If you have an equation and you plug in a -3 and you work it out and you get out a 7, that's your answer, 7. So then you might be confused and say, but wait a minute, here's one where if you plug in a -3, you're not going to get the limit, you're going to get a different answer. Well, what's this equation going to look like? Piecewise, right? I mean, you're going to recognize that the function is something weird. If you get a piecewise, yes, then you're talking about something like this, right? But I'm saying if you have just some normal looking equation like these are here, oops, wrong worksheet. If you've got a normal looking, wrong worksheet. Here we go. If you've just got a normal looking equation like these are, okay, and you plug a number in and you get out an answer, that is your limit, okay? If you've got a piecewise, we're going to talk about a piecewise, then you got another story, right? Then you got another story. All right, so first is substitution. Now, if that doesn't work, probably what happened, if you do substitution and you don't get a number, well, there's only a couple of options, right? Now, somebody asked me in the other class, what happens if you get 0/6? That's 0. That's a number, right? 0/6 is just a number, right? So that's fine. That's your answer. 0/6 is just 0. That's your answer, okay? So you can get a number answer. Step 1, you're done. Well, what are the other things you can get that's not a number answer? Well, the one that you get the most is 0/0. And if you get that, you keep going. Now, the reason that's the one you get the most is because that's where the interesting things happen. To be honest, typically, not always, but typically, that's going to be a hole in the graph. And those are the interesting parts of graphs when we're talking about limits, because that's where the cars meet. Even though the function's undefined there, the cars meet, and so those are the ones that you get on limit problems a lot. Okay? It'd be pretty boring. It'd be easy. You guys would like it, but it'd be boring if we just kept giving you ones where you just plug in and get a number out, and that's the answer, right? So we usually focus in on where something weird is happening. So that's why a lot of these problems that we do on limits are fractions, because that's when we get these kind of undefined, weird kind of things happening, or else piecewise functions, like your book problems were, right? Because that's where they're a little more interesting to talk about. So you just keep going. Factor, conjugate, bow tie, something, right? So that's where you just keep going, right? So that's where most of our time would be spent on these limit problems, would be on one like number 2. You get 0/0. Okay, if we could see the graph, that'd probably be a hole in the graph, okay? And we do this. Okay. The other thing that could happen is you could get like 4/0 or 8/0 or -4/0 or, whatever. right? I mean, I'll just put 4 over 0, but it could be something else over 0. Now, that's different. What that is a vertical asymptote. So they're both undefined. 0 over 0 is undefined, and 4 over 0 is undefined, but they're different. Okay? So when we get this, we usually have a vertical asymptote, and for right now, we're just going to say the limit does not exist. Just stop right there. The limit does not exist. Now, did you have one of the problems where you got 0 over 0, and then you factored it, and then you got a number over 0? Was that number 2?
Yeah.
Number 2, okay? So let's take a look at that one real quick. So on number 2, okay, if you plug in a -1, you get 1 minus 1 is 0. Oh, wait, no. That one you get -2 over 0 right away, don't you? But I'll bet you factored it anyway, didn't you? See, sometimes we get in a big hurry and we don't do the substitution part, right? Because we get so used to getting 0 over 0. Now this one does factor. It factors into x plus 1, x minus 2, and then the bottom is x plus 1, x minus 1. And what happens here is we do that. Wait a minute.
X plus 2 and x minus 1.
Yeah, I did that wrong. It's x plus 2. I was going to say something's not working here. So it's those that cancel. And so we end up with x plus 2, and we end up with x plus 1 here, right? There we go. So we end up with this, and then we put our -1 in, you get 1 over 0, right? Well, either way, it does not exist. You just did more work than you needed to. So when you substitute on that, now was there one though that, oh, it was 3. No, that one's, yeah, it was 3. So you plug a 5 in here and you get 0 over 0, right? So that means keep going. Now, a lot of times that means a hole in the graph, but not always, right? And this is one of those examples. So we go here, we got 0 over 0, so we think, hey, keep going. Something's gonna happen. So you factor it. So you get x plus 7, x minus 5, and then the bottom is x minus 5, x minus 5. Well, those cancel, right? Well, that's good, because that's what was causing the problem, because when we plug in a 5, we get 0. So now we plug in a 5, and we get 12. Oh, whoops, there's still another x minus 5 down there. See? And so we plug our 5 in, now we get 12 over 0. Okay, so we thought we could keep going. We thought something nice might happen. So now we just say does not exist. That's our answer. Now we get to chapter 4, I'm going to make you do a little more. Does not exist isn't going to be good enough. We're going to talk about what's going on. We're going to get into infinity and vertical asymptotes and stuff there. But for right now, you get a number over 0, we just say doesn't exist. Okay, does not exist. All right, so back to here. And so if you get this, you just stop. And then the last one is just piecewise. What do we do with piecewise? Okay, well, we're going to look at the one in the book. But what if they give it to you as an equation? Well, that's like 39 through 42 piecewise? 39 through 42 is a piecewise. Okay, so we'll talk about that when we get to there. And then those you just have to handle, because you know if you have a piecewise, okay, let's face it, that's the only time you're really going to get these weird kind of breaks. And, you know, the only way you can have a graph that's going along and then it stops and then it starts somewhere else and does, I mean, that's the only way is a piecewise, right? I mean, sure, we can get our vertical asymptote kind of problems if we go back to here, right? We get these graphs that come along and they do this and then they do this. And so there's definitely a break there. There's a break in the graph there, but that's because it's a vertical asymptote. That's when we get these things. And the hole in the graph, we've seen these problems with that just have a hole and they keep going. They're aligned. They just have a hole there. And those can happen too. So we can take care of those. But these weird ones that are just have these breaks all over the place, like this, well, that's got to be piecewise. So then we can deal with those. Okay, and we're going to know where those break. Okay, well let's any questions up through number 26? that you want to talk about on this picture here? 16 says the limit as x approaches 2 from the left. Remember that little negative sign up there means from the left, right? So at 16 it says x approaches 2 from the left. So think of a car coming in. Now, you know, somebody in the other class was asking me, they said, well, they were bothered because if that car, it depends where that car on the left starts. Well, over here, he'd be up here and he could never get down. No. That's not what we're talking about. We talk about as x approaches 2 from the left, we're talking about, like, say the car starts here and then it comes in from the left. Where's the car hit? That one. Yeah, that one. It's just really easy. Don't overthink it. Car right there. There it is. Car goes right there.
Wait, so if it doesn't have a negative or a positive, is that just where it means from both ways?
If it doesn't have a negative or a positive, then that means it's a two-sided regular limit. That means it has to come in from both sides. Those are the ones that do not exist. The limits from the left and the right will exist. I mean, those always have a number because a car on one side is going to go somewhere, right? So when you have, so for example, number 18 then, right? 18 says a limit on the left as x approaches 2 from the left. Well, that's 1. Limit from the right as a car on the right approaches. That's 1. So 18, what's the limit as x approaches 2? That means it's at 1. The limit on the left has to equal the limit on the right. So 16, 17 both were 1, so 18 is going to be 1. The cars will be at 1. Unlike here, the limit on the left is 1, the limit on the right is 2, so the limit at -1 does not exist because the cars don't. Okay? Now, you did get in on 24, 25, they were talking about f prime. So now you got to think about slope. Okay? So when you look at 24, -1 from the right, what's the slope? So you got to think what the slope graph would look like. Well, what are the slopes? 0, 0, 0, 0, 0, 0, 0. So 0. So the slopes are approaching 0. Because remember, it's what the outputs are approaching. Well, the outputs of f prime are the slopes. On 26, as x approaches 3. 3 or negative? -3. So as x approaches -3 from both sides, what are these slopes? 1. The slope's 1 here and it's 1 here. I mean, just because you're going backwards, it's not negative, right? I mean, the slope is 1 here. So as we come in here, the slope's 1 the whole time. So the answer is 1. Okay? All right, let's talk about 39 through 42 then. So on 39 through 42, you've got this piecewise function. So it says f of x is equal to, so we really need to understand a piecewise function. That'd be 3 minus 1/2 x squared, and that's when x is less than 2, and then 3x minus 5 if x is greater than or equal to 2. Okay, so now think about this. You have no calculator. Could you graph this and sketch it? Sure. I didn't see a lot of graphs on your paper, but maybe you did. But you don't have to. You don't have to. What is, when x is less than 2, what kind of graph is this? It's a parabola. Is there any weird things there? Are there any holes in a parabola? Are there any gaps, any breaks, any jumps, right? So if you're less than 2, how would you find the limit? Well, plug in whatever number you're at, right? If you're at a number less than 2, so in other words, I don't know what exactly this one looks like, but what we're saying is, over here at 2, you know, this isn't what it is, but let's say we had that. Well, the cars anywhere along here are going to meet. Anywhere along here, the cars are just going to meet at whatever the y value is, right? And what's the graph after 2? It's a line. So that just means after 2, there's a line. So the cars anywhere after 2 where the cars meet, they're going to meet just at whatever the y value is, right? So the only point at all that's of interest to us in this problem is what? When x is, when x is 2. That's the only time something weird might happen, right? So when you do number 39, it says, what's the limit as x approaches 3? You just plug in a 3. But now the question is, where do you plug the 3? It's got to be the bottom one, right? Because it says when x is greater than or equal to 2. So when x is 3, we'd be on this part of the graph. So we just plug in a 3. 9 minus 5 is 4. So the limit would be 4, right? What about when x approaches 0? Well, now we're on this part of the graph, right? When x is less than 2. We're on this part of the graph over here. So we just plug in a 0. 0, 3 minus 0, 3. Right? It's just that easy. A piecewise function, you know where the weird thing's going to happen is where it breaks, right here. Right? Where it switches from one graph to the other. All right. So skip 41 because that's one we're interested in. And 42 says that when x approaches 1. When x approaches 1, we're back up here on the top one again, right? So you plug in a 1, 3 minus a half, 2 1/2. Right? I mean, it's just easy, right? It's just easy. Don't overthink it. Now, what happens as x approaches 2? Okay, so now what do you got to do for this? You got to plug it into both. Because what we're trying to, in other words, again, say you don't have this graph. Well, what are the two things that could possibly happen in a piecewise function? When this graph ends and the other one takes off, what are the two options for the other one taking off? It's either going to take off from this same spot and be connected, or it's not going to be connected, right? So the key is, what we want to know, even though I know this top one doesn't include 2, that just means it's an open circle. But what I need to know is, what are the two y values at 2? Are they the same? Then it's connected. If they're not the same, it's not connected, right? It's that easy. It's that easy. So we plug in a 2. 4 times a half is 2. 3 minus 2 is 1. Plug in a 2. 3 times 2 is 6. 6 minus 5 is 1. Aha. They're connected. So what is the limit for 41? 1. In other words, when this one takes off, when this one ends, the other one takes off. So we don't have this situation. We have this situation. So the cars actually meet. So this one's coming in at 1, and the other one takes off at 1, at a y value of 1, then the cars meet. So that's it. You're going to run into this. But matter of fact, I have an optional IXL one we can do where it's this exact same thing. Matter of fact, let me show you that right now. So if I go onto my this I section right here on continuity, I got a couple of them that you don't need to do, but right down here it says determine the continuity of a piecewise function, and we're going to talk about continuity here in a minute. But is the function continuous at -6? Well, that just means continuous would mean that they take off from the same point. This would be continuous. If there's a break, then it's not continuous, right? So, bottom line is the function continuous at -6? Well, -6 is where it breaks. So, less than -6, we just have a y value -12. We haven't to do anything. And then here we put in a -6. -36 plus 18, that'd be -18. So, it's not continuous. Because this one is at -12 up until -6. And then the other one's down at -18 when it takes off. So, there's a break there. There's a gap. And so, we'd say no, and we would be geniuses. Is a function continuous at 2, right? I mean, that's the question. It's going to be continuous everywhere else. It's just a line, and then it's another line. So those are fine. The key is there a break there? Okay, so we come back to our quiz review. So that's how you'd handle a piecewise, right? The only place a piecewise is going to have an interesting limit at all is going to be where it breaks from one graph to another, especially if the other graphs are nice and continuous graphs and, parabolas, lines, stuff like that. Okay?
So how's it break in the comments from the second one?
Well, okay, really good question. Okay, so now, what if you plugged in a 2 and got a 1? Okay? And then you plugged in a 2 here and got a 7. Well, what's that mean? It means when x is less than 2, it's coming in here at 1, and then it's taking off up here at 7. Right? That's what that would mean. Okay? So, what would be the limit as x approaches 2? you'd say does not exist because the cars aren't meeting. But what if it said the limit as x approaches 2 from the left? What would it be? From the left would be when x is less than 2. That'd be from the left, so then it would be 1. From the right, it would be 7. But the limit as x approaches 2, you would say does not exist because they don't meet. Okay, good question. Yeah, so if they do meet, it's just that number. If they don't meet, they're different, then you say it's not continuous on that other worksheet. But here, what's the limit? You'd say does not exist. But it would have a left-hand limit and a right-hand limit. And so back to your question, though, you notice I didn't really even care which one it included, right? That didn't matter. For limits, it doesn't matter. It doesn't matter where this one's the included one or this one is, right? It didn't matter in my picture if this one was filled in or this one was filled in as far as the limit goes. What it's approaching doesn't matter, okay? For the function value, it does, right? For the function value, like on this one, if I said what's f of 2, what would you say? I mean, let's assume, I know they're both 1. Let's assume this one was 1 when I plugged in a 2 and this one was 7 when I plugged in a 2. I said, what's f of 2? You'd say 7, right? Because that's the one that I included. Now, I know it's not 7, but just pretend, right? So if I said, what's f of 2? You'd say 7, right? But what if then the line was there and not here? Then I said, what's f of 2? Then you'd plug a 2 into this one, and then it would be 1, right? That's when it would matter, what the function value is, right? But that's different than the limit, right? That's different than the limit. The limit's where the cars are, okay? All right. So that's the book problems. Back to the worksheet. We kind of been jumping around here a little bit. I know we started talking about the worksheet, and then we went to these. Okay, so conjugate. Okay, when you get a radical, now again, you plug in a 9, you get 0. You plug in a 9, down here you get 0, so you always do that first. You get 0 over 0. Then you're supposed to multiply, whenever you have a radical, you multiply top bottom by the conjugate, right? Which is that. On this one, I know it's big and messy, but it doesn't matter. It's just radical plus radical. So you got radical minus a radical. You're going to multiply by radical plus a radical. Now the top's big and messy, but you're not going to multiply it out. You just put it up there. Okay? So you just multiply by those two things. Okay? Now what happens on the bottom here when you multiply this? And these could have been flipped around. It might not be the bottom that simplifies out. It might be the top. It just depends. Whichever one you're doing the conjugate of. Okay? What do you get down here on the bottom? X minus, not 3, x minus 9. This is that one we were talking about. You got 9 minus x up here. We're going to take out negative. And then you still have that radical x plus 3 up there. Right? But these can cancel, but you'll have a negative out there. Right? If you take out a negative, then that turns that into x minus 9. Okay, so you're going to have a negative. Now we can plug in our 9. So radical 9 is 3. 3 plus 3 is 6 with a negative on it. There's your answer. On this one, when you multiply at this bottom, you're going to get x squared plus 12 minus 12, right? Because this radical times that radical is going to be x squared plus 12. This radical times that radical is just going to be 12. The 12s are going to cancel. You end up with that on the bottom. The top is messier, but we don't care. Just write it. Just write it down. Because look what happens. When those 12s cancel, now you can cancel those x squared. See? And now you can put your 0 in for x. So you put your 0 in for x, you get square root of 12 plus square root of 12, which is 2 square root of 12. As far as I'm concerned, you can leave it. It would actually simplify down a little more into that, but whatever. Okay? And then the bow tie, we'll just run through the bow tie one more time. When you bow tie these two things, when you got fractions like this, you start with the top left. So that'll be 5 minus x. And then a minus, and then you do the top ones. And that'll be 5 plus x, but you better get it in parentheses. And then the bottom, when you bow tie the bottom here, you got 5 plus x, 5 minus x. Okay, now when you distribute this, 5 minus 5, those are going to cancel, and then you're going to have negative x, so this gives minus 5 minus x. So the 5's cancel, but negative x minus x, you end up with negative 2x. And then down here, you just have this 5 plus x, 5 minus x, which I'm not going to mess with. And then don't forget, I got this 3 over x sitting here on the outside. Well, that's the good thing, because those x's are going to cancel. See, that's what I wanted to happen. Those x's are going to cancel. Now I can put my 0. By the way, I didn't multiply this one out, did I? Let me do this. So 5 plus, so if I put in a 0, I get 5 plus 0, which is 1/5. And I have 5 minus 0, which is 1/5. 1/5 minus 1/5 is 0. And then I put a 0 here. So what I had was, let me put that in blue. So when I did my substitution, some of you might have been wondering about this. So we really had that when we did our substitution. Okay, we really had this. So you might be wondering, well, what is that? Well, think of it this way. Put that as 0 over 1. Now multiply across. What do you get on top? 0 over 0. Right? So this one is still a 0 over 0. So you keep going. So I don't want to forget that. You always should do your substitution first. Same thing on this one, 0 over 0. Right? That one's going to be 0 over 0. Okay? Well, anyway, now that the x's cancel, now we can put in a 0. So you put a 0 in there, you get 5. Put a 0 in there, you get 5. 5 times 5 is 25. So you multiply the top, so you get negative 6 over 25. Just like that. And then, of course, this one's just your FOIL that out. Nice things happen. Matter of fact, that's a lot like, matter of fact, that is. This is what we're going to talk about today. This is like number 34 and 35 on the homework the other day. Isn't that one this one? Except the x is in place of what over there? The x is the h, and the 2 is the x here, right? But look at it. It's 2 plus, think of this as 2 plus h cubed minus 2 cubed all over h, and limit as h approaches 0. So this is just like one of those we did when we did the cube ones, right? So, matter of fact, we might as well just go into that now because we're pretty much done with the homework. So one of our goals today, okay, so we've done these first two, evaluate limits graphically, so we talked about that, and we had those homework ones with the thing there. But now, what do we do with the calculator table type problems? What do we do with ones where we want to use a calculator? And then we're going to do some that we're going to do some limits where, like problem 34 and 35, you look at them and they have a special look to them. They were special limits. They were this limit. They were the definition of derivative. Remember, the rest of this page didn't have anything to do with derivatives. These are just limit problems. These are just limit problems. Where do the cars meet on this function? Right? That's all they were. This is a special one. This is actually a derivative problem. Okay. This would be the, well, let's just do it real quick. What would be the function that this would be doing the derivative of? What function would this have been that would have fit into here that would have been our f function? X cubed. And we'd have been doing the derivative at 2, right? Because that's where the 2 was right there, right? The 2 is right there. So we've been finding f prime 2, but hey, we have this cool thing called the power rule. By the way, what did you guys get for number 8? You got an answer? You got 12? Should have got 12, right? When you worked it out. Well, we know the derivative of x cubed. What's the derivative of x cubed? 3x squared. Now put a 2 into that. You get 12. You get 12, right? The derivative of x cubed at 2 is 12. When you work out this limit problem, you got 12. Because this limit problem is, because of its special look, is the definition of derivative. Okay? Matter of fact, this, why not? Let's pull this up. Let's see. I wasn't planning to do this, but it seems like the right thing to do right now. AP test, AP release, for exam, I can't find it. This is last year's AP test. This is the international test. This is the one that they gave overseas because the time changes, so they get a different one. Okay, but it's very similar.
Look at that. Question number 3. Limit problem. Oh, it's infinity. We haven't done infinity. Oh, look at that. Slope of the tangent line. We can do some of this. Oh, that's not infinity. Here's a function with the derivative. Where is it? F decreasing, right? Chart question. We can do that. Oh, look at this, 11. We can do 11. There's F. Which of the following would be F prime? What would you be looking for? You'd be looking for a graph that's what? Negative, positive, negative, right? Negative, positive, negative. Would it have to be B? Have to be B, right? Just like our decimals match. Okay. All right, we're getting there. I think this is the no calculators. Come on, okay. There it is. There it is. There's always one. There's always one. Look at this. This is no calculator, right? This is no calculator. So you look at this and it'd be like, ooh. Oh, okay. You'd look at this problem. Oh, that's a twist I've never seen before. That's interesting. I'm glad we did this. You'd be going along, and trust me, this is easier now than it'll be later, because later we won't have done this for a while. But people, what'll happen is you'll try to plug in a 0, and you'll get 0 over 0, and you'll be going like, oh my God, what do? I don't have a calculator, I can't do any of this. But what you have to recognize is, hey, this is just a derivative, right? That'll be the thing you'll have to recognize. You have to say, hey, that looks special. That's this, right? So what function is it? It's e to the x. Now, the only thing I noticed that was a little funky here was they had minus h. But think about it. If I'm going to do my derivative at -1, my second point I could go over h. But couldn't I also go this way h? Right? Couldn't I have, when I set that up, couldn't I have done f of x and f of x minus h? Well, why would you want to? Why put in a minus if you could do a plus, right? So we never do a minus, but that's what they did. That would freak some people out probably. They'd go, wait a minute, that's supposed to be plus h. Minus h would be the same thing. So it's still the derivative. And then so what's the derivative of e to the x? It's its own derivative, right? And what number are we doing the derivative at? -1. We're doing the derivative at -1. So you put a -1 in here, you get e to the -1, which is a negative, right? And just that. E to the -1 is 1 over e. There's your answer right there. So it's really intended to be a quick, easy problem. You know, you get a couple minutes for each one of these problems if you're going to need it, but some problems you might need more than that, so it'd be nice to have some easy ones. Well, this is supposed to be an easy one. This is supposed to be one you read and you just go, hey, wait a minute. That's a special limit. Looks like this. It's e to the x. The derivative of that's e to the x. Plug in a -1. Boom, there it is, and you're done. Okay. So there's always one of those. Seems like every year. Okay, I'm afraid I wasn't going to find one here, but it seems like almost every year there's one of those where you're just recognizing this special derivative. Okay. So we're going to be doing a worksheet that's going to have some of those where there's a bunch of those like that that have that special look to it. Okay. All right. So go ahead and get. Pass those out. Put your hats on there. Okay, go ahead and log in. Skylar is the presenter. Might not do too much. All right, first thing I want you to do is, so let's go to the graph screen. And yeah, let's go up there to F1 and delete that out of there. Okay, so now let's take a problem where we just can't do any algebra to it. So let's say I have the limit as x approaches let's say 3 of oops. Let's say we had this right here. I just made this up. Okay? I hope it works. Okay? So, if we were going to not use our calculators on this one, there's no algebra to do, right? We can't do anything with ln 4 minus x. We can't distribute. It's not ln times. It's a function. It's ln of 4 minus x. We have x minus 3 on the bottom. We can't do it. If we plug in a 3, what's 4 minus 3? What's ln of 1? You got to know that. You got to just spit that out immediately. Here's the ln graph. ln of 1, 0. What's ln of e? ln of e is 1. ln of e is 1. ln of 1 is 0. You got to know those. ln of 1 is 0. And then 3 minus 3? 0. We get 0 divided by 0. Right? Now, so we're going to talk about how we can find this limit. Now, if we had a graph of it, we'd be in great shape, right? If we had a graph of this thing right here, we'd be in great shape, right? We could probably tell. So that's what we're going to do. Now, a little side note here. While Skylar's on here, hit enter, Skylar, just so we get rid of your old graph, and hit your scratch pad key again. And let me show you where this will do limits. So go over here to this button next to the 9, and grab the limit template right there. We hardly ever do this. We hardly ever use this, because I'm hardly ever going to ask you. The limit problems on the AP test are always no calculator. I am on Wednesday's quiz. I'm going to have you do some with your calculator, but I'll show you what we're going to do. Doing this isn't going to do you any good. As a matter of fact, sometimes on the calculator, when I just tell you what the limit is, but then you're going to show me the table that proves that's what it is. So you'll see in a minute. So go ahead and put an X there, and then put a 3 there. Now, if you wanted to do from the right or from the left, right, you could put in a little plus or a little minus there, but we're not going to put it. And then go in here, now do a fraction, so go hit Control Divide, and then let's put in our ln, there you go, what was it, 4 minus x, and then on the bottom, let's do x minus 3, and then hit enter, and aha, we get an answer, right? I mean, so there is an answer, but the best we can do when we plug in a 3, we get 0 over 0, right? So the idea is keep going. Well, there's no algebra we can do, so I wouldn't give you this one on an algebra. So what am I going to want you to do on your calculator? Okay, so hit your scratch pad, go to your graph again, and let's actually graph that fraction. So go hit Control Divide by. Now, we're not graphing the limit and all that. We're not graphing that. We're just graphing the ln 4 minus x part, and we want to see what's happening as x approaches 3. There you go. So we want to graph that. Okay? So we graph it, and everything looks fine, but of course if we trace at 3, go ahead and trace at 3. We know that, we already know that
something weird is happening, right? It's undefined. There's a hole in this, right? So we can tell, though, that the cars are approaching something. So here's where we're going to do that table. I think I showed it to you the other day. Hit Control T. Control T for table. And there you get a table. Now, problem is the table's not set up right. Okay, we want to see what's happening when the X column is close to what? Is everybody getting these same numbers like this? Okay? Because if you're not, go to the menu real quick. Go to menu. And go to table. And go to, well, it doesn't really matter here. Well, that's where I want you to go anyway. Go to table settings. So you go to menu, you go to table. Now this is with the table highlighted, right? You might have to use your thumb on the trackpad so you can go back and forth between your graph, because if the graph is highlighted, then your settings, when you go to menu, it'll look different, right? So you have the table highlighted. So where do we want our table to start? At 3, because it's as X approaches 3. So we want our table to start at 3, and then this, I would go like 0.001. I would just put a couple of zeros. You don't need more than a couple, and then leave those others off. Okay? And now scroll up once or twice, and here's what you're going to do. You're going to copy down on your paper and move your cursor up. Click up there somewhere so this goes away. There you go. And then what you're going to do is you're going to literally copy down on your paper that table. Okay? And I'm going to want at least a couple on each side. Okay? So if this is 3, so this would be my X and this would be my Y, whatever. And so this would be 2.999, and this would be 2.998, and this would be 3.001, this would be 3.002, right? And then this was undefined, and to be honest, we don't care about that. Of course it's undefined. It was 0 over 0. But what else do we see in our table, in Skylar's table? We see negative 0.999, okay, negative 0.9990. We see negative 0.9995. Here we see negative 1.00, I can't remember. What was it? 1.005, and then scroll down a little bit so you can see another one. So go over here to the table again, and then scroll down, and then 1.0010. So in your table, you'd have negative 1.005 and negative 1.0010, like that. And that is your proof to me that this is a problem. Look at it. It's kind of like the cars coming in here, right, on your table, right? Negative 1, a little less than negative 1. Over here on the right, this would be the right, okay, of 3. And they're a little more than 1, okay? Well, more, I guess. They're below negative 1. But they're coming in towards negative 1, so we can tell, we can see there's visual proof there. And this is what I mean by using a calculator table. So this would be used on one where there's no algebra to do, right? So what you do is you graph this part of it, and then you look at the table. So on the test, I might give you this. I might just give you that. I might just say, hey, this limit is equal to negative 1. Prove it with a calculator table, right? So you'll get on your calculator, you'll graph this, and set up your table correctly, and then you'll put that table down on your paper. And then that table is showing. Now, if it doesn't show, you might need a few more decimal places. You might need to put a few more decimal places if you can't show for certain that it's heading towards negative 1. Okay? That kind of thing. Now, what would happen in a table? What if this one was going towards positive 1, and this one was going towards negative 1? And then here it was undefined. You would say does not exist. That's the cars not meeting, right? On this side it's coming in a negative 1, this side is coming in a positive 1. You would say does not exist. That could happen. You might get these could be positive 0.999, and this would be negative 1.0, right? And this one's coming in positive 1, it's coming in negative 1 on the other side. They're not meeting. Cars don't meet, right? So I want you to be able to see these in a variety of ways and understand what's happening, right? So I want you to be able to do them with the algebra that we talked about. I want you to be able to see it with a table of values, graphically as well. All those things, okay? All right. And then finally, I want you to be able to see it with the the ones that are kind of like derivatives. I'll show you here. So we're gonna, so here's, oh, shoot, we're not ready for that. I'm sorry. I got one last thing I gotta show you. Turn in your books. One last thing we gotta put in our notes, and then we'll, let's start with it. Totally forgot about mine. Yeah. All right.
Calculus relies heavily upon the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you could even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these, g, h, and I, they're not continuous. Each of them, in fact, is discontinuous for a different reason at the x value of x equals c. See, now this one, on g, you've got a little hole in the graph. That's called point discontinuity. Over here on h, you've got a vertical asymptote that breaks the graph. Now this is called infinite discontinuity. And finally here on graph I, you've got a graph that just plain snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other functions, I'm either going to fall through or fall off.
Okay. Now, we're not talking about
So,
limits here. We're talking
continuous
about
functions are
continuous.
predictable. But what does that mean? Well, it means two big things. One, no breaks. Well, we already know that breaks occur in functions when no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit. How can you tell if this happens? It seems pretty complicated. It's actually easy. If you can evaluate any limit on f of x using only the substitution method, then the function is continuous. And that's all there is to it.
Okay. So, bottom line, and he said there at the end, if you can just substitute and get it at every point on there, then the function continues. But more so, function's continuous if you don't have to lift your pencil. He talked about holes, breaks, whatever. But we're gonna identify that as three parts. Now he had up on the thing, he had that little equation. Well, there's three parts to that equation. So what would make a function not be continuous? Okay, so continuity. Let's talk about, or let's say continuous. Oh, that's spelled wrong. Another U. Continuous functions at x equals a. So we're talking about at a point. Now, to be a continuous function, it has to be continuous all the time. Or if we say, is the function continuous on this interval, then it has to be continuous at all the points in between there. Okay, that kind of thing. So there's three things that has to happen. F of a, he was using C, but f of a must be defined. Okay, there has to be an output there. Okay, so for an example, here would be an example that would violate that, right? Here would be an example that would violate that, either that or a vertical asymptote, right? So those functions are clearly discontinuous at that point, right? you'd have to lift your pencil, there's a gap, there's something weird going on. Continuous, again, just think connected. Continuous means just connected the whole time, okay? This right here, they called that a point discontinuity. Here they call this an infinite discontinuity. Don't worry about those terms. So those two situations would violate, okay, number one. Number two, the limit of f of x as x approaches a must exist. Now notice how we use the term defined when we're talking about a function, and we use the term exist when we're talking about the limit, okay? So the limit must exist. Now, examples of that, these go up here with the first one, okay? Examples of the limit not existing would be something like this. And it would also be the vertical asymptote example, right? The vertical asymptote example, the limit wouldn't exist either, right? If you had a vertical asymptote, the cars don't meet. So here's two situations where the cars don't meet. There's really no other situation where the limit doesn't exist. I mean, limit doesn't exist, like he said, a break in the graph. If the cars don't meet, the limit doesn't exist. So the function is clearly not continuous. It's not connected, okay? And then the third thing is those two have to be the same. The limit as x approaches a of f of x has to equal f of a. In other words, and this is something we talked about earlier today, that the cars might meet at one place, but the function value might be some other place. Okay, and so that's this example right here. Right? That's that situation. Okay? Because think about it. This situation, the first two are okay. Right? In this situation here, in this situation, the function is defined. It's got an output right here. The limit exists because the cars meet right there. But they're not the same. Where the cars meet has to be the same as the function value. Okay? So for the function to be continuous, it must have all three of those parts. Now, they only gave you this last part. Well, for the limit to equal the output, that's kind of like saying the output must be defined, there must be an output, there must be a limit, and they must be equal. So the first two are just saying, okay, we must have this, and we must have this, and then they also must be the same. So on the quiz on Wednesday, I'm going to give you some, maybe a piecewise function, because obviously where most of the time, something weird's happening via piecewise function. So a lot of times with continuous, we use piecewise function. But if I gave you a piecewise function and gave you some questions and said, why is this discontinuous? Or I might say, where is it discontinuous? And then say, why is it discontinuous? Don't say a jump, a break, an asymptote. Don't say that. I want you to say one of these three. So you're going to need to know these three. So if we go back to this problem we had here, why is this discontinuous at -1? I mean, clearly this is not continuous at a lot of spots, right? Everywhere it's not connected, it's discontinuous. Why is it discontinuous right here, -1? Limit doesn't exist, right? It violates number 2. Okay, I don't want you to say it violates number 2. I want you to write the limit does not exist. Okay, what about here at let's hide this point right here. Pretend this point isn't here. Why? Can't really hide it, can I? Pretend this point isn't here. So at 2, why is this discontinuous? Violates number 1. The function's not defined. There's no output at 2. Right? That's why I'm covering this up. Okay, now let's pretend it's not covered up. Now, why is that discontinuous at 2? It violates number 3. The limit exists, which is 1, and the output is defined, the function's defined, which is at -1, but they're not equal. So it violates number 3. Okay, so we have those examples in there. We won't get into the vertical asymptote ones very much because we haven't talked much about those, but more like that. Okay, so that's what it means for continuous functions. Okay, so you're going to have some questions about that, I think, in your homework as well. All right, so our homework, we've got this worksheet, front and back. Okay, You've got, in section 2.3, we're gonna do, I think it's on your homework sheet, it's down there a ways, a couple lines down. We're gonna do 61, 63 through 67, so I am jumping around on the homework sheet here a little bit. So we got the worksheet front and back, okay? We got section 2.3, we got this right here. And then optional, now the IXLs, now don't forget about those optional IXLs that I gave you the other day. I didn't even check to see if anybody did them. But those gave you some algebra practice on limits and stuff. These optional ones give you some questions about continuous functions. So it's section I. It's section I that I showed you there. And you can skip I3 and I7 for sure. You could do any of the other ones. Again, it's just optional practice for, okay, on the IXL. All right, so last thing then would be on the worksheet. So let's do one more. Let's do one on the worksheet together. Okay, and we'll let Skylar do this one. So what are we doing on number? This is on the side that says calculator limits. Now both sides are calculator limits. By calculator limits, I mean you're just doing these limits using a calculator table. It says evaluate the following limits using your calculator. What I mean is by a table. If the limit does not exist, it says check the one-sided limit. So like that example I gave you, if it was 0.5 on one side and negative 0.5 on the other side, then you would write that down, that it didn't exist. Okay, so on number one, so we go to our calculator. So Skylar's way ahead of me. She's already typing it in. Okay, so she went, hit your tab key and show everybody again there, Skylar. So she's got it typed in. Oops, that's okay, just scroll down. There we go, that's fine too. Okay, hit your right arrow. I wonder if your right arrow, there you go. Okay, so she went ahead and typed that in just like that. Don't type in the limit part of it, right? You just type in the function. Just type in the function that because you're looking at its y values as x approaches, what is it on this one, 0? So now go over to your table. So now she needs to highlight her table. So once you have that typed in, now Control T will get rid of the table. Control T back and forth will put the table up and get rid of the table. Okay, but click over your table. Now we don't want the table to start at 3 this time though, right? We want the table to start at 0, so you can't forget that. Okay, you always want the table to start, and a lot of these are 0. So once you get the table set, matter of fact, all of them are 0 but 1. So, but don't forget, they're not all as x approaches 0, but this one is. And so you start your table. That's in the menu when your table's highlighted. Okay, go ahead and hit OK. And what's it look like this one? Arrow, and then arrow up a little bit. So what's it look like this one is? Looks like 0.5. So on your worksheet, I want you to copy down that table, okay? So I want you to copy down that table. That's why I gave you this room here. I want the 0 would be right in the middle, and it was undefined right there, okay? And then I want a couple of values on both sides, and then give me the answer too. And the answer is 0.5 or 1 hand. Yes.
Can you do that one without a calculator? Or wait, I'm on the other side.
Okay, I'll go to the other side. But to be honest, could we have done this one without a calculator? Yes. We could have done the conjugate method here, right? We could have done the conjugate method on this one. There's maybe some algebra we could do on some of them, but I don't want you to, right? I just couldn't come up with enough of them that, didn't have some algebra. So I wanted to give you some examples. So on this side, do them all with the table. Just get used to that. Now, I'm sorry. Let me interrupt you one more time. Let's go to the back side then. Here we go. So on the back side where it says limits and derivatives. Okay, this is a side where I just want you to write. Well, I still want you to do basically the same thing, but I want you to. And I'm not going to get real picky looking at your tables on this side. On the other side, for sure, I want you to do tables on all those. On this one, if you just want to type in and get the answer, whatever, that's fine. But I may ask you one just like this on the quiz where I want you to do the table, right? Now, tell me this. Well, first of all, what function is this then? This is the 2 to the x function. What a value are we looking at? It's the derivative at 3, right? We're doing the derivative at 3. Now, when you go to put this into your calculator, because I'm going to probably ask you what's similar to this. How would you put this on your calculator? Because this is what you would type into your calculator, right? Not 2 to the x, but you type this into your calculator. Well, you can't type in h's, right? You'd have to replace the h with x. So in your calculator, you'd have to type in this, like that, right? And then you would look as x is approaching 0 on your table, right? And then put a table. I prefer for you to put a table on this side too. I mean, because for sure you're going to do that. I want you to get real comfortable with that. But the difference is every one of them on this side look like this. They look like the definition, right? They're all special limits that have been purposely set up to represent derivatives. All right, so you got the rest of the time to work on it. Anytime you give a decimal answer, 3 decimal places. Now this one came out, this, as far as the limit on that one side, it was 0.5. But in the table, you mean how many? As much as you can see there, if it's 3 or 4 or whatever. Hopefully you can see 3 or 4 decimal places. There's not a lot of room on the table to see.
What if like on 2, like it's